Hey folks, in this video we are going to be studying a property of waves in general called wave superposition, and this general wave property is going to turn out to make some really interesting light phenomenon happen for us. So here is the cool thing that we're leading up to with this. Sometimes when you take some light and you add in more light, you take some light, you add some light, you get more light, right? Turn on two lights, it's brighter than just having one light on. Sometimes. But also sometimes, when you take light and you add light in, you get darkness. Sometimes light plus light equals dark. It's crazy. It's wild. Let's talk about what I mean with that. Wave superposition will be able to explain what I mean. Here I have two waves that I'm adding together. We have wave 1 plus wave 2. They line up nicely. The crest lines up with the crest. The trough lines up with the trough. Wave 1 plus wave 2, their sum is the big wave, which has the same wavelength, but twice the amplitude. The amplitudes added together. So this is the case where light plus light equals brighter light. Sometimes though, so the resultant here is twice as bright because waves 1 and waves 2 are in phase. Sometimes you go to add two light waves together, like waves 3 and 4 here, and those light waves are not in phase. So we have crest of wave 3 lining up with trough of wave 4, and then we have trough of wave 3 lining up with crest of wave 4. And when you add those two waves together, your resultant B here is complete darkness. And that's because waves 3 and waves 4 are 180 degrees out of phase with each other. So you take those two light waves, they're out of phase, you add them together, you get darkness. The next slide has an animation of this. The top slide, or the top wave is stationary, we slide the second wave along, and then their sum is shown below. We see that when the waves are in phase, we get a bright big wave in the end. When they're out of phase, we get darkness. Then when they're somewhere in between, the sum is somewhere in between the 0 and max. So that's adding waves in general. You can get anywhere from 0 to twice the amplitude depending on the relative phase of your two waves. So now, and my little bubble is going to be in the way, two waves, we're going to look at the conditions through which constructive and destructive interference happen. So constructive interference is when they add up together to give you a bigger wave. Destructive interference is when they subtract to 0. So two waves are in phase and they constructively interfere when the difference in their path lengths, delta L, is a whole integer multiple of the wavelength of the wave's wavelength lambda. Let's talk about what I mean. We've got two waves here in blue, and we're going to add them together. And we're going to focus on point 1 here and point 2 on the second wave below. Right now, these waves are going to add together and constructively interfere. If I shift wave 2 over by one wavelength of the wave, these waves are still in phase, and so they're still going to add. So we get this constructive adding interference because the amount that I slid point 2 over, the delta length, is equal to one wavelength of wave 1. But what if I slid point 2 over here? And now point 2 is two wavelengths away from point 1. But we'll notice that the waves still line up. So these waves would still add together. So we still get constructive interference, and this occurs with a path difference, delta L, of 2 lambdas. If I slide over wave 2 again to a point where the amount it's been slid, the path difference delta L, is now 3 wavelengths, we're now again at a point where constructive interference happens. If I slide it over to 4 wavelengths, the same thing happens. If I slide it over to 5 wavelengths, the same thing happens. So we get constructive interference whenever the path difference between your 2 points, delta L, is 1 wavelength, 2 wavelengths, 3 wavelengths, 4 wavelengths, etc. The pattern is that constructive interference happens when the path difference between your 2 waves, delta L, is some integer multiple of the wavelength lambda. So this is generalizing what's on the left here. M is any integer plus or minus 1, plus or minus 2, plus or minus 3, etc. The negative takes into account that I could have chosen to slide point 2 to the left instead of the right. What about destructive interference? 2 waves are 180 degrees out of phase and they destructively interfere when the difference in their path lengths, delta L, is a half integer multiple of the wave's wavelength lambda. What do I mean? As shown right now, we would get constructive interference because the waves line up. But if I shift P2 over just half of a wavelength, now the waves are out of phase. The trough of the top wave matches up with the crest of the bottom wave. And this is shifting over just half of a wavelength. So we get destructive interference when the path difference delta L is a half wavelength between the 2 waves. Now, when is the next point where P2 would destructively interfere? Think about that for a second. At which point, next point will P2 destructively interfere? Well, now it's got to slide a whole wavelength over here so that it can line up with the next. So the crest of point 2 could line up with the trough of the top wave. So we are now 1.5 wavelengths away from point 1 to get another point of out of phase destructive interference. We slide over another wavelength, that's where the crest of 2 will meet the trough of 1 again. So 2.5 wavelengths gives us destructive interference. 3.5 wavelengths also gives us out of phase destructive interference. So does 4.5 waves, and that's it. And so on, I mean. Now that's not it, but it keeps going. So in general, destructive interference occurs when your path difference between your 2 waves is some half integer multiple. You take your integers, 1, 2, 3, 4, positive, negative, and then you add on a half, right? At a half a wavelength, 1.5 wavelengths, 2.5 wavelengths, 3.5 wavelengths, so on. I'm just realizing I don't have 0 in for M, but 0 is allowed too. All right. So, what does wave interference do for light? Total constructive interference means your light is twice as bright, twice the intensity. Total destructive interference means the 2 light waves sum to make darkness, or in practice, it's usually very dim light. Here's a Desmos animation of the same idea. Let's open that up. So, what's going on in this animation? I'll let you just look at the screen for a moment and then I'll describe it. All right, in this animation, let me go ahead also and make it projector view. The sort of transparent background waves, the red and the blue, those are 2 light waves that we're adding together. And then the purple is their sum. It's what happens when you add the 2. And then we are looking at how bright the light would be at the origin. And so we can see that brightness is varying between 0 and 2. We're going between 0 intensity and twice the intensity of either of the individual waves in that background. And then how bright the light you see is represented by the size of that red circle. So we wouldn't actually see a growth in the size of the light, but we would see it getting brighter and then dimmer. and then brighter, and then dimmer. And we can see what happens, right? The brightness happens when the blue and the red overlap, and then the darkness happens when the blue and the red are out of phase with each other and crest lines up with trough. So that's our wave interference. We get different amounts of brightnesses and darknesses depending on how the light waves act. Light plus light does not always mean brighter light. I believe that concludes our wave superposition slides. We'll talk more about experimental evidence with wave diffraction for lights in future videos.